Hello everyone, welcome to today's chemistry class. Today we discuss the topic polarity of bonds. So here we discuss the polarity of bonds, how the bonds are getting polarized. The existence of a 100% ionic or covalent bond is an ideal situation. In reality, no bond is either completely covalent or ionic. Even in case of covalent bond between two atoms, or example two hydrogen atoms, there is some ionic character in that. That means the 100% covalent bond or covalent character and ionic character is an ideal situation. It is not real. That is the point. So here we discuss the polarity. When covalent bond is formed between two similar atoms, like examples hydrogen, oxygen, chlorine, nitrogen and fluorine, the shared pair of electrons is equally attracted by the two atoms, or we can see the shared pair is equally distributed between the two atoms. As a result, the electron pair is situated exactly between the two identical nuclei. Okay, the bond is so formed is known as non-polar covalent bond. That means there is no distinction in the electrons. Electrons are equally shared. Okay, and when a bond is formed between two different atoms or heteronuclear molecule like HF or HCl, the shared electron pair between the two atoms gets displaced more towards the electronegative atom, more electronegative atom. Here in HF it is fluorine. It is far greater than that of hydrogen. Here electronegativity of fluorine is very much greater than that of hydrogen. So the shared pair of electron is shifted to or displaced to the fluorine atom. The resultant covalent bond is a polar covalent bond. So when a covalent bond is formed between different atoms, two different types of atoms, the shared pair of electron is shifted to or displaced to more electronegative atom. So we get a polar covalent bond. As a result of this polarization, the molecule possesses a dipole moment that is depicted below, which can be defined as the product of the magnitude of the charge and the distance between the centers of the positive and negative charge. It is usually designated by a Greek letter mu. It is represented by a or depicted by a Greek letter mu. It is pronounced as mu. Mathematically, it is expressed as mu, that is dipole moment, is equal to charge into distance of separation or charge into distance between the atoms in the covalent bond, that is D. Okay, so mu is equal to Q into or mu is equal to E into D. E means charge, D is distance. Okay, dipole moment is expressed in dBi units, capital D, dBi. The conversion factor is 1 dBi is equal to 3.33564 into 10 power minus 30 coulomb meter. Here C is coulomb, M is meter. Coulomb is unit of charge. Meter is a unit of length. That we have studied. Okay. Now, for the dipole moment is a vector quantity. I think you have studied in physics. Vector quantity has both magnitude and direction, and scalar quantity has only magnitude, no direction. Okay. It is a vector quantity and is depicted by a small arrow with a tail on the positive center. It is depicted by a small arrow and tail on the positive center and the head pointing towards the negative atom. That means the arrow pointing towards the negative atom and the tail ultrapositive atom. Okay, for example, the dipole moment of HF may be represented as HF എന്ന് കൊടുക്കുക, tail Hലുണ്ടായിരിക്കും, arrow Fലുണ്ടാകും. Okay. Okay, in case of polyatomic molecules, the dipole moment not only depend upon the individual dipole moment. So in case of polyatomic molecule, the dipole moment depends upon the different atoms. Okay, so here in case of polyatomic molecule, the dipole moment not only depend upon the individual dipole moments but also the bonds, moments of bonds known as bond dipoles, but also on the spatial arrangement of various bonds. So in polyatomic molecules, it does not depend upon the dipole moment of individual atom but also the spatial arrangement, the spatial arrangement of various bonds. In such a case, the dipole moment of a molecule is the vector sum of the dipole moments of various bonds. Here vector sum of the dipole moments of the various bonds. Here it depends upon the spatial arrangement and the direction of the bond. Here dipole moment of polyatomic molecule is depends upon the individual dipole moment as well as the spatial arrangement, that means direction of that particular bond. Okay, for example, in H2O molecule which has a bent structure, okay, the two OH bonds are oriented at an angle of 104.5 degree. Net dipole moment of 6.17 into 10 power minus 30 coulomb meter is a resultant of the dipole moment of two OH bonds. Okay, that is the dipole moment, that is 6.17 into 10 power minus 30 coulomb meter is the resultant of the dipole moments of two OH bonds. That is the dipole moment of water. Peter Debye and Dutch chemist received Peter Debye, the Dutch chemist, received Nobel Prize in 1936 for this work on X-ray diffraction and dipole moment. Okay, it was the dipole moment and studies were conducted by it was conducted by Peter Debye, and he got Nobel Prize for the same in 1936. The magnitude of the dipole moment is given in Debye unit in order to honor him. It is named after him to honor Debye. Okay, net dipole moment mu is equal to 185 Debye, that is equal to 185 into 10 power minus into 3.335 into 10 power minus 30 coulomb meter. Okay, in the case of water, mu is equal to 185 Debye, that is 185 into 33564 into 10 power minus 30 coulomb meter. In the case of water, this is the value 6.17 into 10 power minus 30 centimeter. Clear? Sorry, it's not centimeter, coulomb meter. The dipole moment in case of beryllium fluoride is 0, BeF2. Dipole moment in the case of beryllium fluoride is 0. This is because the two equal bond dipoles point in opposite direction. കാരണം രണ്ട് ഡൈപ്പോളും ഓപ്പോസിറ്റ് ഡയറക്ഷനിലേക്ക് ഡയറക്റ്റ് ചെയ്യപ്പെട്ടിരിക്കുന്നു. So they cancel out the effect each other. So they cancel out the dipole moment. In tetraatomic molecule, for example, BF3, the dipole moment is 0, although BF bonds are oriented at an angle of 120 degree to one another. The three bond moments give a net sum of 0 as the resultant of any two is equal and opposite to the third. Okay, so here BF3 also has 0 dipole moment because of the structure or the orientation or the spatial arrangement of molecule, atoms in the molecule. So BF3 has 0 dipole moment. Okay, now this is a very important point we are going to discuss. In case of NH3 and NF3 molecule, both the molecules have pyramidal shape. Here both the molecules have pyramidal shape with a lone pair of electrons on nitrogen atom. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of ammonia, the orbital dipole due to lone pair is in the same direction as the resultant dipole moment of NH bonds. Whereas in NF3, the orbital dipole moment is the direction opposite to the resultant dipole moment of the three NF bonds. The orbital dipole, because of lone pair, decreases the effect of the resultant NF bond moments, which results in the low dipole moment of NF3. So we will discuss, we can explain this. Okay, here although fluorine is, this is NF3, we are going to discuss the two compounds NF3 and NH3. Okay, NF3 and NH3. Here in NH3 the dipole moment is 1.49 dB. In NF3, in nitrogen fluoride, the net dipole moment is 1.49 dB. But in case of NF3, only 0.25 dB. In NF3, dipole moment is 0.25 dB. By what is the reason for this? Because fluorine is more electronegative than hydrogen, but the dipole moment is very, very less when you compare with NH3. So we can see the reason for this. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of ammonia, that is 1.49 dB, is greater than that of NF3, nitrogen trifluoride, that is 0.25. What is the reason? Both NH3 and NF3 have pyramidal shape, and the central atom has a lone pair, that is nitrogen has a lone pair. In NH3, the orbital moment due to lone pair is in the same direction. So you can see the orbital moment due to the lone pair is in the same direction. Lone pair ന്റെയും അതുപോലെ തന്നെ ഹൈഡ്രജൻ നിന്ന് നൈട്രജനിലേക്കുള്ള ഡൈപോൾ മൊമെന്റ് എല്ലാം ഒരേ ഡയറക്ഷനിലാണ്. ഓക്കെ, ആസ് എ റിസൾട്ട് the dipole moment of 3 NH bonds hence adds on the resultant dipole moment. അപ്പോൾ NHൻ്റെ എല്ലാം ഒരേ ഡയറക്ഷനിലേക്കാകുമ്പോൾ അതിൻ്റെ എല്ലാം ഡൈപോൾ മൊമെൻറ്റ് ആഡ് ചെയ്യപ്പെടുന്നു. ഓക്കെ, so here in NH3 the orbital moment due to lone pair is in the same direction as the resultant dipole moment of 3 NH bonds hence adds on the resultant dipole moment of NH bonds. ഓക്കെ, അതായത് ലോൺ പെയറിൻ്റെ ഡൈപോൾ മൊമെൻറ്റും 3 NH ബോൺസിൻ്റെ ഡൈപോൾ മൊമെൻറ്റും കൂടെ ആഡ് ചെയ്യപ്പെടുന്നു ഒരേ ഡയറക്ഷനിലായതുകൊണ്ട്. സോ ഇറ്റ് ഹാസ് എ ഗുഡ് ഡൈപോൾ മൊമെൻറ്റ്, അല്ലെങ്കിൽ കൂടുതൽ ഡൈപോൾ മൊമെൻറ്റ് ഉണ്ടാവും. ഹൗവർ ഇൻ NF3 the orbital moment due to the lone pair is in the opposite direction to the resultant of 3 NF bonds and hence partially cancelled by each other. So here in NF3 ഫ്ലൂറിനാണ് ഹൈ ഇലക്ട്രോനെഗറ്റീവ്, അപ്പോൾ ഫ്ലൂറിലേക്ക് പോകും ഡൈപോൾ മൊമെൻറ്റ് അല്ലെങ്കിൽ ഇലക്ട്രോൺസ്. സോ ലോൺ പെയറും എൻ്റെ ഡയറക്ഷനും ഡൈപോൾ മൊമെൻറ്റ് ഡയറക്ഷനും ഫ്ലൂറിനിലേക്കുള്ള ഡൈപോൾ മൊമെൻറ്റ് ഡയറക്ഷനും ഡിഫറൻ്റ് ആയിരിക്കും. സോ ദേ ക്യാൻസൽ ഔട്ട് ഈച്ച് അതർ, partially cancelled by each other. So the dipole moment of NF3 is less than that of dipole moment of NH3. So this is a very important question. Although fluorine is more electronegative than nitrogen, the resultant dipole moment of ammonia is greater than that of NF3. What is the reason? Okay, the reason is in NH3 the direction of dipole moment is same as that of the lone pair, and here in NF3 the direction of dipole moment is different. Okay, it is different and they partially cancelled out by each other. That is the reason for this. Okay, now we can see the dipole moment of some molecule and the geometry of the molecule also. Here molecule is AB type. First of all we discuss molecule AB type. AB type means only one A atom and only B atom. HF dipole moment 1.78, geometry linear. HF means hydrogen fluoride. HCl hydrogen chloride 1.07, it is in dBi, linear geometry. HBr hydrogen bromide 0.79, that is dipole moment is 0.79 dBi, linear. HI is hydrogen iodide, that is 0.38, linear. Okay, here electronegativity decreases, dipole moment also decreases. And H2, it is a non-polar covalent molecule, so dipole moment is 0, linear geometry. Then molecule AB2 type, that means one atom has 2 number and another atom has only 1 number, that is AB2. Here H2O, dipole moment 1.85 dBi, structure or geometry bent. H2S 0.95 dBi, bent geometry. Carbon dioxide 0 because the linear. Okay, linear shape, they cancel out each other. Okay, the dipole moment cancelled each other. Molecule AB3 type, first of all NH3 1.47, trigonal pyramidal. NF3 0.23, trigonal pyramidal structure. BF3 has 0 dipole moment, that we have already discussed. Okay, the next one is molecule AB4 type. AB4 means one atom has 4 numbers and another atom is only in 1 number. CH4, because of this geometry, okay, spatial arrangement, CH4 has 0 dipole moment, tetrahedral geometry. Tetrahedral, that we will discuss geometry and the hybridization, all the things we discuss later in this chapter. CHCl3 is known as chloroform. CHCl3 is chloroform. 1.04 tetrahedral. CCl4 0 tetrahedral. Okay, so today we have discussed polarity of bonds. Polarity is nothing but when two atoms are bonded to form a compound. One atom is electronegative, highly electronegative, then the shared pair is shifted to that atom and the bond is getting polarized, and that atom gets a positive small negative charge, other gets a small positive charge. So bond is getting polarized, so dipole is formed there, positive and negative, and the measurement of the quantity of dipole is known as dipole moment. It is expressed in dBi. Mu is equal to E into D. Mu is dipole moment, that is charge into distance. Mu is equal to ED. Okay, that is a thing that these are the things we discussed here. Polarity of bonds and why NH3 is having more dipole moment than NF3. Nitrogen trifluoride has a low dipole moment when you compare with ammonia because of the direction of the dipole moments. Okay, that is all about today's topic. Thank you.